Hello guys, welcome back to Introduction to Number Theory. Now, I would like to discuss the number of solutions of the Pell's equation. But first let me remind you what Pell's equation is. It is an equation where x squared minus a times y squared should be equal to 1. Well, we have something like 3 variables here, but actually only x and y are unknown. And a is also an integer, but it's a certain integer. We do not try to find it. We just simply take it and consider such an equation. It depends on a. So let me just write this. These are unknown. And this one is, so to say, known. Okay, so when we just look at this equation, we actually do not know whether it has solutions or not. Well, my goal now is to show that if there is a non-trivial solution, then there are infinitely many non-trivial solutions. No, I wasn't correct when I said that we do not know whether it has solutions or not. Well, there is one obvious solution, which I simply do not think of as a solution. Well, if x is equal to 1 or minus 1 and y is equal to 0, then obviously such pairs are solutions of the Pell's equation, and this is what we call trivial solution. And the question is whether there are any non-trivial solutions, and actually how many of them are there. Now I will show you that if there is at least one non-trivial solution, then there are infinitely many non-trivial solutions. And it would be easier for you to understand if I take a particular example of a and show you with this particular number. So usually we use a equal to 2. So let's just say that a is equal to 2, and I may assure you that everything that is going to be happening from this moment on can be applied to any a whatsoever, except for those that are perfect squares. May I remind you that we call this equation the Pell's equation only in case where a is non-square, which means that a is not equal to the square for any integer d. Okay, so consider a equal to 2. Well, 2 is certainly not square. Then we have an equation, x squared minus 2y squared equal to 1. Are there any non-trivial solutions of this equation? Well, I think that thinking for less than a minute will let you come up with a non-trivial solution. Say x can be equal to 3 and y can be equal to 2. Well, actually 9 minus 8 is actually equal to 1. So this is a non-trivial solutions. Can we think up of any other non-trivial solutions? Well, of course, we can elementarily put minus before 3 and minus over here before 2, and we already have 4 non-trivial solutions. But are these solutions interesting for us? Well, I don't think so, because we have square here and square there, and actually plus or minus, it doesn't matter. So let's try to construct some more solutions using this one. For that purpose, let us write down the decomposition of the left-hand side into factors. Well, at first sight, we don't really understand how could we decompose it into factors, because, well, we are trying to work inside the ring of integers. But if we step out of the ring of integers and use even some irrational numbers, then the left-hand side can be decomposed as x minus square root of 2 times y and x plus the square root of 2 times y. So this should be equal to 1. So this is another form of the Snell's equation. And in this form, it will be much easier for us to conduct and to construct the infinite number of solutions. So these two equations are the same. Now, put particular values instead of x and y. So we have 3 minus 2 squares of 2 multiplied by 3 plus 2 squares of 2, and this is by all means equal to 1. Having this expression, we can raise it to any natural or even negative integer power whatsoever, and it will still remain true. Now we understand that 1 to the power of k is always 1. And what can we do about these two factors? The first factor, when expanded, can be represented in the form a, well, plus or minus, I will write minus b square root of 2, where a and b are some integer numbers. I believe this is rather obvious. Well, you can try and be sure that this is so. What about the second factor? Well, expanded, it can also be represented in the form integer plus or minus some integer times square root of 2. But actually, and I think you understand why this is so, it is equal to a plus b square root of 2. So integers in the representation of the first factor are exactly the same as the integers in the representation of the second factor. The only thing these integers depend on, except for the particular numbers, is the power. So we can write that ak and bk over here and ak and the same to ak and bk over here. So these ak and bk depend on k, which is the power to which we raised this expression. These ak and bk will obviously be different for different k. So we have infinitely many solutions of our equation. And now I would like to show you some of these solutions just to be sure that these are new solutions, not old. Well, say if k is equal to 2, then 3 minus 2 squared to 3 minus 2 square roots of 2 to the power of 2 is equal, let me now just calculate, this is 9 and this is 8, so it is 17, and this is 3 times 2 is 6, so minus 12 square roots of 2, and of course we understand that 3 plus 2 square roots of 2 to the power of 2 is equal to 17 plus 12 square roots of 2. And this is exactly what I meant when I said that integers in the expansion of the first factor are the same as the integers in the expansion of second factor. Well, this is in the previous terms, this is a2 and this is b2. And we have another pair, 17, 12. And this is another solution of the Bell's equation. X is equal to 17 or minus 17. We understand that the sign does not influence anything. And y is equal to 12. Well, if you don't trust me, and I hope you don't, because this is mathematics and we need to check everything, then we can check this pair of numbers. Well, 17 squared is equal to 289, and 12 squared is equal to 144, and multiplied by 2 is actually 288, which is just by 1 less than 17 squared. So this is indeed a solution. And then we can take k equal to 3 and k equal to 4 and so on, so on. And 3, 4, and so on. And this will give us new and new solutions. So from this point, it seems that there are infinitely many solutions. And the only thing I would like to say about, before we can be certain, 100% certain that this is so, is why these new solutions never coincide with the old solutions. I mean, we really have some sequence of A's and some sequence of B's, but could these A's or B's repeat in these sequences? Well, now I state that they do not repeat. But why is this so? And I believe that easiest way to really prove that they are really new and they do not repeat is to notice that, well, 3 plus 2 square roots of 2 is actually greater than 1. And 3 minus 2 square roots of 2 is actually less than 1. So when we take this number and raise it to some power, we get new numbers, and new and greater numbers and greater numbers, so they never repeat. From this it follows that AK and BK are also new and different for every power to which we raise this number. And now we can be 100% certain that there are infinitely many solutions of the Bell's equations. And let me once again assure you that never mind what number would be here instead of this number 2, the same story would hold. So if we have one solution of the Bell's equation, then we have infinitely many of them. Whether there is or not a solution and what is the structure of solutions, it is another question, and we will discuss it in another fragment.